Right, staff, thank you for joining me once again, where we continue to deal with charlatans. We continue to deal with walking examples of Dunning Kruger syndrome on feet. We continue to deal with people who think that reading published research written by others is somehow going to make you competent in your own right as someone who can sensibly, remotely, critically analyze a piece of literature, its underpinnings or its meaning, and make reasonable and sensible prognostic statements as a result of those readings. I'm sorry, Mike Fave, but it doesn't. For those that don't know, Mike Fave is a Ray Peat acolyte and as such a fool of the highest order, someone without sufficient capacity to discern good science from pseudoscience and nonsense to make a reasonable statement about anything. Mike is also qualified as a nurse. Nothing wrong with that, but it's a perfectly fine profession with a fine tradition. However, it does not qualify you, Mike, as a scientist or as someone who is remotely qualified and credentialed to speak with any kind of authority on science, despite which you suffer from a sufficient degree of Dunning Kruger to believe otherwise, and as such it leads you to make videos like this one, which we're going to critique today, wherein you attempt to make an argument, but it falls flat on its stupid face because of your inability to actually critically look at a situation holistically and understand its place in the universe. And as such, you make a ridiculous and reductionist argument that will not work for you, son. Sorry about that. Anyway, let's deal with it. So Mike Fave and his mate Jay and their mate Roddy made a video this week about things I had said about the Randle Cycle, wherein they promised to point to things I got wrong about the Randle Cycle, and they brought absolutely nothing to the table. They made absolutely no points about anything that I might have had wrong about the Randle Cycle, or in fact anything else, actually. They giggled inanely like a bunch of prepubescent schoolgirls. They behaved like Beavis and Butthead all rolled into one, each and every one of the three of them, and they failed utterly to make a single scratch on my armoury of actual knowledge in this area. And as part of that, Mike has put together this video wherein he basically puts together his idea about what the Randle Cycle is and what its ramifications are. He puts forward an interpretation of the thing, despite having said the other day in the video with his little mates that it's not open to interpretation. Nonetheless, he's provided an interpretation. The interpretation he's provided is reductionist. It's incomplete. Much of what he has to say is correct, but completely irrelevant to the argument at hand. And much of what he also has to say backs up what I have had to say about what the Randle Cycle is and what its ramifications are. In fact, so what he's doing is actually bolstering my argument here in this video, not undercutting it in any way. So well done, Mike. Good work, you absolute buffoon. And once again, may I remind you, son, that the bedpans are not cleaning themselves. There is nursing to be done, son. I think you should go and do that rather than trying to do my job, which is sensible and qualified commentator upon the science. Okay, anyway, let's hear what you have had to say about the Randle Cycle, and we'll put it right where it's wrong and make other commentaries along the pathway as I see fit at the time. So, off you go.
Welcome everyone, Mike Fave here. Today I'm going to go through what exactly is the Randle Cycle.
No, what you're going to do, Mike, is talk about aspects of the Randle Cycle, selected aspects of the Randle Cycle, as interpreted according to an ideology and a principle by certain authors, those being the ones on the screen here. What does it say? Hugh and Tegmeyer. okay? And you're going to mindlessly espouse what these people have had to say, their interpretation of it. And what you're also going to do is leave out half of the discussion on what the Randle cycle is and how it works and what the ramifications are. Well, more than half, actually. So, no, you're not going to talk about what the Randle cycle is at all. So there's your first mistake. False.
So on the most recent Bioenergetic Healthline number 8, Jay, Danny, and I were discussing some of the issues with Bart.
No, you weren't discussing. What you were doing was giggling, as I said, like prepubescent schoolgirls and behaving like children and failing whatsoever to actually provide any information of utility or point to any errors that you proposed that I was making. You talked about my errors, but you didn't lead to that discussion, didn't lead to you pointing to any errors at all. None.
Kay's description of the Randle cycle. And we didn't really dive into the specific mechanisms of the Randle cycle.
No, you didn't at all. And as such, your video was a complete failure. This video that you've made here is an attempt to get into aspects and mechanisms, and it fails as well, Mike, for the reasons I've just outlined. It's reductionist, it's incomplete, and you are leading people to a false and inaccurate conclusion on the basis of what you've had to say here.
We kind of glossed over and discussed them.
No, you didn't. You said NAD, NADH, FAD, FADH, citrate, and stuff, and giggled inanely. I'm not exaggerating. Those that haven't seen that video, I've done a full response to that video here on my Fine channel, which you can also watch at your discretion.
Or more specifically, discuss the parts where Bart was at least incorrect from our perspective on the.
Not incorrect from any perspective. Everything I've had to say about the Randle cycle is demonstrated, supported with research, and is known phenomenologically. It is correct. And I am unassailable on what my interpretation of the Randle cycle is. You had a go anyway. You failed completely with your little mates, and you failed again in this video, Mike. Completely. Off you go, though.
The Randle cycle. So I wanted to take you guys through today the actual mechanisms of the Randle cycle.
Hang on. You're going to talk about the actual machinery, the actual metabolic machinery, the thing that you said does not exist, Mike, on that video, that the other thing you were laughing inanely about, as if that was some kind of point-scoring mechanism. And now you want to talk about that very machinery, the actual physical underpinnings of the Randle cycle, the components of it that cause the effect known as the Randle effect. Which is it, Mike? Can you not see you're eviscerating yourself here? No, you probably can't because of your very, very severe case of Dunning Kruger. Right.
We'll go through some graphics, show you how carb oxidation blocks fat oxidation. I'm going to start.
Yes. Carb oxidation can block fat oxidation. And fat oxidation blocks carb oxidation. Well, not blocks. Inhibits. It's very important that we actually get this right. It's not a blockade. Well, up to a certain level, it's not a blockade. It's an inhibition. Once the inhibition level reaches 100% in any given cell, then it is a blockade at that time until that inhibition is released by that cell's mechanisms, machinery. Jay. Mike. Okay? You buffoon.
Start out by using a research article here, the Randle cycle revisited, a new head for an old hat.
Right, so your evidence here that you're underpinning the basis of your video on here, Mike, is a review article, i.e. someone's opinion. This is not an experimental piece of work at all. This is an opinion piece. Where do opinions sit, by the way, on the treasured hierarchy of evidence? Just to clear that one up before we get too much further. Oh, yes, that's right. Right down the bottom as not a good source of evidence of anything. This is somebody's interpretation, Michael, of the Randle cycle. Okay? There are also other papers available for balance if people want to look at those. Also, there's common sense for people that have some of that they can apply to understand what it is that the Randle cycle is, what it's designed to do, and how effectively it does it. I'll cover that, though, in this discussion.
That's the title of the article. And I'm going to show you some graphics just so we can break down and you can actually see what is going on, at least theoretically, in the mitochondria with...
Yeah, and again, referring to the Randle cycle or the Randle effect as being in any way limited in scope to a mitochondrial thing is false. It is reductionist. The Randle effect, mechanistically, cause and effect, precipitates activities occurring within a given cell on the whole cell level. It is not a mitochondrial piece of kit. It is a cellular piece of kit, machinery, Mike.
Carb oxidation being blocked by fatty acid oxidation. So we're going to start off here. I'm not going to read every single element of the article. I'm going to pull out the relevant points.
You're going to pull out what you think are the relevant points out of their context, and then you are going to reductively misinterpret actually what this paper is about and what it does and does not infer or imply.
And what we're going to initially discuss is what exactly is the Randle cycle, and there's a good sentence here, and basically...
Who says it's a good sentence, Mike? That's your interpretation. I thought this thing wasn't open to interpretation. Oops, there's another mistake from you, Mike.
Randle cycle can be described by inhibition of glucose utilization by fatty acids. It is...
Right, it can be described that way. It can also be described as the exact opposite, because at the same time, the exact opposite is also true, Michael. It can be described also as the utilization of glucose inhibiting fatty acids, and the other way around. It does both. What it means is that there is a cross inhibition. The oxidation of, well, not even the oxidation, the provision of acetyl coenzyme A to the Krebs cycle via glycolytic means can cause an inhibition of the provision of acetyl coenzyme A to the Krebs cycle from the oxidation of fatty acids. The provision of acetyl coenzyme A from the oxidation of fatty acids can inhibit the provision of acetyl coenzyme A from glycolytic sources. And both things are simultaneously true. It is a cross inhibition. One locks out, inhibits the other at the same time. So this is a completely unbalanced view on what the Randle cycle is, and a reductionist view on what the Randle cycle is, looked at monoscopically from one angle only, while ignoring entirely the other equally valid angle. And as such, this is not a good paper to use as a basis for a discussion on what the Randle cycle is, Mike Fave. Sorry about that.
It's a form of glucose intolerance that resembles or may lead to insulin resistance, i.e. the impaired...
Insulin resistance is a concept. It is a construct. It is a way of describing or attempting to provide an underpinning explanation for differential responses to the exact same concentration of glucose in the blood of a person from time to time. It is, however, not a physiological fact or existence or thing. It is a concept. We need to be very, very clear on that. The thing that is measured, or the things that can be measured, are the concentrations individually of glucose in the blood and insulin in the blood. We can also measure the production rates and disappearance rates of both glucose and insulin using very expensive, very scientifically technical kit. Yes, but that's almost never done. What we are measuring, if we are measuring anything, is blood glucose and blood insulin. Okay? Not insulin resistance, which is a concept. All right?
capacity of insulin to increase glucose uptake by muscle and adipose tissue, accompanied by increased lipolysis and increased hepatic glucose production.
Not necessarily. That can occur under certain physiological circumstances, but it is not a fait accompli. It is not a cause and effect set of phenomena.
So, quick translation here. Fatty acid oxidation at the cellular level blocks glucose utilization by those...
No, it doesn't block it. It inhibits it, Michael. That is a very different thing. At a certain level, if you get enough fatty acid being oxidized in a cell, that will 100% inhibit glucose. Then it's a block. At 99.9%, it's an inhibition. Important point, important distinction. The same is true of sugar. At a certain level, it will 100% inhibit fat oxidation. But right up until that point, it's an inhibition. Okay, blockade is 100%.
Same cells that are burning fatty acids, burning in quotations.
Yeah, well, they're not.
This leads to a form of glucose intolerance that could be a feature of insulin.
Glucose intolerance. That's a value judgment statement. That's not a scientific word. That's not an empirical descriptor. Intolerance. Intolerance is the sort of thing I have for bullshit coming from charlatans and completely unqualified fuck muppets like you, Mike. Okay? The human body becomes inflamed and damaged by an exposure to a concentration of sugar which is above that which is physiologically indicated. As such, the body has mechanisms to protect various tissues from that damage from sugar, preferring instead to put up sacrificial lambs or sacrificial pawns in their place. And the important tissues like the muscle cells, etc., cells of the various important organs and things, are protected from that damage by the effects of the Randle cycle doing exactly what it should do. And the sacrificial pawns, the sacrificial lambs, are the red blood cells, the white blood cells, the vascular epithelial linings, etc., which can all be replaced much more quickly and with much less difficulty by the human body. As it was, we evolved in such a way that there was very little carbohydrate around. It was very rare for a human being to consume a large bolus of carbohydrate, and as such, the problems associated with that are, or were, not really consequential to that human across a lifespan. Now, however, we live in a society where we are encouraged to eat tons and tons of carbohydrates every single day. And obviously I'm exaggerating with the tons and tons. Shitloads is what we're encouraged to eat. Far more than is physiologically indicated. The physiological indication, the requirement for exogenous carbohydrate in the diet of human beings is not a single gram ever, not 1 gram. We are perfectly capable of providing all the glucose we require for a long and healthy lives ourselves from non-glucose precursors. Okay? Those are the facts. Sorry about those. Anyway, move on, Mike. Make some progress.
Resistance in pathologic situations. And essentially, you also will see increased lipolysis or releasing of fatty acids into the blood.
Not necessarily in the situation where the Randle effect is in effect, where the Randle cycle is in effect, I should say. It's not a fait accompli at all.
Bloodstream and increased production of liver glucose, or the production of glucose by the liver in this state. So there's kind of a lot going on here, but the key point is that fatty acid oxidation blocks glucose utilization.
No, it doesn't. It inhibits it. Wrong again.
Or glucose oxidation at the cell. That's essentially the Randle cycle. There is the
No, it isn't. That's one aspect of the Randle cycle. That's one of the things, one of the effects of the Randle cycle becoming activated. If it is activated by a large amount of beta oxidation, then the result is an inhibition to glucose oxidation. The same is true on the other side, which you're completely ignoring here, Michael, in your little video. And that is a large amount of glucose oxidation will inhibit fatty acid oxidation. Okay, don't forget that. That's important.
Opposite effect, where glucose oxidation can block fatty acid oxidation to some extent, but the most major piece here to discuss is the inhibition of glucose utilization by fatty acid oxidation.
Why? Why would that be the most important thing to discuss? Unless you have an ideology whereby you think it's a requirement for some reason to consume carbohydrates in large amounts every day, in which case, if you did believe that, which would be foolish because that's wrong, we don't require a single gram ever, then you would understand that the Randle cycle actually is a good thing. And as such, you would avoid mixing your macronutrients up in your diet, and you would avoid fats, which would be a mistake long term because you need a bunch of nutrients that you will only find in fatty animal products to be healthy and have a good degree of longevity, Mike. So it's not looking good for you at all.
That's the main point that I'm going to talk about here today.
The main point, it's the only point you're going to make. And it's correct. A large amount of fatty acid oxidation will inhibit glucose oxidation. And there is a reason why that occurs, and it's precisely in order to protect the homeostasis and the functioning of the cell as a whole, and to protect it from glycative damage, which I'll explain when it becomes relevant a bit later in this video.
Because I think it is one of the most important ones in this whole carb versus fat debate that we're seeing with the keto, carnivore, paleo, bioenergetic spheres, etc. So let's actually dive into the mechanisms.
Those mechanisms that don't exist, Mike, because it's not a piece of kit, it's not a piece of machinery. Mechanisms. Machinery, physical things, various enzymes. The actual components of the Randle cycle that lead to the Randle effect when the cycle is activated in a certain way, one way or the other. Good. Thank you for eviscerating yourself and showing everybody watching this video what an absolute fool you are for having laughed stupidly saying, it's not a piece of metabolic machinery. Yes, it is, Michael. Because you're just about to start pointing to those components. Those physical things, the things that make up that machinery. You buffoon.
So basically they continue here, and what they're talking about in this section is that glucose is spared and rerouted.
Okay, those two words are also value judgment statements. Spared? That makes out that glucose is in some way a limited resource and requires protection against utilization for some reason. It's neither of those things. It doesn't need sparing. Your body is capable of producing all the glucose it needs, and it does so incredibly effectively. It's called gluconeogenesis. Perhaps next time you look at Wikipedia, Mike, your favorite research engine, you might read up about that and learn something. It's very, very effective. It's evolved over 13.8 million years, billion years at least. 13.8 thousand million, that is. Funnily enough, that's long enough for that to be a very effective system that works really well. So glucose does not need to be spared. Glucose use is inhibited, and it's inhibited for a very good reason, which we'll get to in a minute. Okay? Well, in however many minutes it takes to get to that bit. The bit that you've completely missed, Mike. The bit that you also claimed in your video the other day that I had wrong in some way. Dear oh dear.
During fatty acid oxidation. And this is actually a survival mechanism when the
the integrated holistic functioning of cells as a whole, and therefore tissues as a whole, therefore organs as a whole, therefore organisms as whole, are all survival mechanisms. They have all evolved over a long period of time. What is your point?
When you don't have adequate carbohydrate, glucose, other forms of carbohydrate.
Human beings have adequate glucose at all times, produced by the human body at all times. The only time you're going to have a human being that's short on glucose is a human being with type 1 insulin-dependent diabetes who has either injected too much insulin or has consumed not enough counterbalancing carbohydrates to offset that insulin that they, in natural circumstances, wouldn't be taking in. It's a human invention to inject exogenous insulin into a human body. Okay. Pretty straightforward.
Such as fructose coming in from the diet.
So now you're saying that there is a level of sufficiency of carbohydrates in the diet. That is false, Mike Fave. The exact physiological requirement in human beings for the intake of exogenous carbohydrate is not 1 single gram ever. The caveat being type 1 diabetics who are forced to do so because of the medical intervention, the exogenous and unnatural poking in of insulin, which has to be counterbalanced with an appropriate bolus of things for that insulin to work on. Okay.
Or fatty acids. And what winds up happening is that this process basically inhibits glucose oxidation and spares that glucose.
No, that's absolute nonsense. That's an interpretation. Glucose does not need to be spared in that manner whatsoever. The reason the Randle cycle exists is to protect cells from the damage that they would otherwise suffer because of a concentration of glucose in the cell which is too high. And it does that by knock-on downstream effects of the Randle cycle, which I parsimoniously refer to as the effects of the Randle cycle, because that's what it is, which you have totally and not only failed to address in your video here remotely, competently, fully, or with any understanding of the actual holistic mechanisms of a cell, Mike, but you've also denied the existence of these things and said that my description of them is nowhere near what the Randle cycle is. In your arrogance and your Dunning Kruger and your absolute error. And as I say, I'll point to those things soon.
For the central nervous system and other tissues that directly rely on carbohydrate. That could be the gonads, adrenal glands, red blood cells, but
explaining the existence of gluconeogenesis, which maintains the function of those organs irrespective of the amount of intake of carbohydrates in the diet, in all but, for example, type 1 insulin-dependent diabetics, who are a special case.
But specifically the central nervous system, that's the main one to discuss, and that it requires a decent amount of glucose on a
What's a decent amount, Mike?
Regular basis. So it is absolutely essential that the body has glucose for the central nervous system. So
that's why we have gluconeogenesis, Mike, because it serves that purpose, absolutely.
So the rest of the body will essentially run on fatty acids to allow the central nervous system to oxidize that glucose. So what they...
It's almost as if the body has a homeostatic mechanism that protects itself from demise and provides for appropriate functioning throughout the lifespan. Whoops. That's what it does.
Say here is by inhibiting glucose oxidation, fatty acids and ketone bodies so contribute to a glucose sparing effect. And
no, it's not sparing effect. Glucose does not need to be spared. We've covered this.
Essential survival mechanism for the brain during starvation. So this is essentially what I just...
No. Starvation has nothing to do with this.
described. When you don't have enough glucose on board, fatty acid oxidation.
Well, except for type 1 diabetics with too much insulin and not enough carb, everybody has sufficient glucose on board.
Takes precedent in the vast majority of tissues, sparing that glucose
No, it doesn't need sparing still.
For the central nervous system, which absolutely requires glucose to function appropriately.
And that's why it gets it, and that's why it does continue to, in most people, Mike, function appropriately, does the central nervous system. Unless, of course, you poison yourself with a toxic overburden of carbohydrates, which can cause severe brain fog, severe problems understanding your own level of incompetence, i.e. Dunning Kruger, and eventually will lead you to very, very serious health failure. But that's yet to come for you, Mike. You'll discover that when you get to it.
Even with ketone production, which the central nervous system can use ketones, there's still a large percentage of glucose oxidation that will occur even with ketones present.
Yes, that's correct. And it does that, and it does it perfectly effectively. It needs no assistance from exogenous carbohydrate supply, none at all.
So the ketones are a survival mechanism as well?
No, they're not really. Well, they are in that they are a part of the normal holistic functioning of the human metabolic pathways. They're actually more a signaling second messenger hormone-like response, which gives the cells of the body information through the medium of the blood as to the energetic state of the body, and as such elicits various responses hormonally, etc., that lead the body to maintain its homeostasis all the more effectively.
As is the rest of the body using fatty acids and sparing.
As it should, and it's not sparing
that glucose for the tissues that need it. So they continue further here. They say, the glucose fatty acid cycle is not restricted to the fasting state and is readily observed in the fed state after a high-fat meal or during exercise.
Or also during a high-carbohydrate meal. See how they've left that out completely? Because it's just as valid and just as important to understand that the Randle effect is the cross-inhibition. It is not simply the inhibition of one thing by the other. Goodness me, Mike, you really are a buffoon, aren't you?
When plasma concentrations of fatty acids or ketone bodies increase, under these conditions, part of the glucose that is not oxidized is rerouted to glycogen, which may explain the rapid resynthesis of muscle glycogen after exercise.
Yep, great. No problem with that. So what?
Rerouting of glucose towards glycogen also explains the increased glycogen content in muscles found in starvation or diabetes. So something important that's kind of implied here is that during fasting, when you have a lot of lipolysis or release of free fatty acids because you don't have adequate glucose coming in exogenously.
You do have adequate glucose coming in exogenously at all times, because the exact requirement for glucose intake at all times is not 1 gram ever.
The body will essentially upregulate fatty acid oxidation, and this will spare some glucose.
No, it doesn't spare glucose. It inhibits glucose oxidation in the cells.
Well, so it's not just eating a high-fat meal that can lead to increased fatty acid oxidation. States such as fasting, where you have to rely on your...
It's almost as if the human body is designed to run on fat and does so effectively, having evolved along those lines continuously over a period of at least 13,800 million years, Michael.
Your body stores of nutrient or substrate, fats and carbohydrates, states where you've used a large portion of or you've used a decent portion of your carbohydrate readily available and have started to undergo lipolysis, like exercise. Another state would be...
So now you're suggesting that lipolysis only begins to occur once the carbohydrates are used up, which is also false, Michael. Wrong again. You clearly, for someone who's qualified as a nurse, you seem to have almost no understanding whatever of integrated holistic functioning physiologically of the human body. How is that possible, Mike? How could you be so lacking in competence that you don't understand this even?
Stress would increase all of these states would increase plasma fatty acids, and those plasma fatty acids could impair glucose oxidation, or essentially spare glucose oxidation.
No, not spare.
Something that they talk about here that's a little bit tangential to the overall picture that we're talking about.
This is what I'm talking about. Just because Michael reads the words "it spares glucose" on a page, he thinks that that's some kind of inviolate canon and that it's correct. It's not. This is an interpretation written by these two authors ignorantly and reductionist manner. That is, as in looking at one aspect of the Randle cycle in isolation to its actual place in the universe. Nuts.
Talking about is that in states where there's heavy amount of lipolysis and fatty acid oxidation, that glucose won't necessarily be oxidized. So it actually, again, it gets spared and it can...
You've said that I don't know how many times already, and it's still fucking wrong, Michael. No.
Be rerouted towards glycogen synthesis since it's not being used. And so you can find this situation in starvation or in diabetes. Both states are...
Yeah, you've said that too.
Characterized...
And I said, so what? And I'm going to say it again. So what?
By high amounts of fatty acid oxidation.
So?
When then paired, surprisingly in starvation, when then paired insulin sensitivity.
This is possibly around an assertion made by Danny Roddy in their little chat the other day where they giggled like schoolgirls, that he was inferring that I had claimed that the only thing that affects the Randle cycle is the macronutrient makeup, I should say, of the food, which I never said, ever. I never said anything remotely similar to that because it's not correct. And what Michael is saying here is correct, but it's reductionist and it's irrelevant to the discussion around the Randle cycle and what it is that human beings should consume in their diet, which is the overall arching moot here. What should human beings eat ideally for their health and longevity? This discussion, this rambling, reductionist description of various components of the Randle cycle, human metabolism, whatever, does not elucidate Mike. Also, it's somebody's interpretation, which is a fundamentally flawed interpretation. And you're a buffoon and a charlatan. You are Dunning Kruger on feet.
Sensitivity to some extent because the body is releasing so much fatty acids and oxidizing so much fatty acids that, as we discussed above, up here, that will inhibit glucose utilization and can lead to...
Yes, that is correct, but so what?
Insulin resistance. Now...
No, not insulin resistance. That's a construct. That's a concept. The thing that is observable is a reduction in the rate of the oxidation of glucose. Nothing to do with insulin, and I'll explain why that is so soon.
Insulin resistance...
No. Concept, construct, fantasy.
There's like you can break it down. It's not a perfect...
See what I mean? Now he's going to start wanting to talk about insulin resistance and he has no idea what he's even going to say next. He's falling over his own feet. He doesn't have the first clue of what he's talking about or even what he's going to say.
It gets a little sticky, but you can break it down in terms of physiologic insulin resistance.
What does that mean? That's just a descriptor label. Okay, so what you're now going to suggest is there are different types of a fantasy? This will be good.
And pathophysiologic insulin resistance.
Right, so a value judgment statement. Useful so-called insulin resistance and unuseful so-called insulin resistance. How do you define which is which, Mike? And how do they differ exactly? What bit of kit do you put on that? How do you measure which one of those is useful and not useful?
Pathophysiologic insulin resistance is what you see in diabetes.
Right, no, what you see in diabetes, the pathophysiology of diabetes, is elevated blood sugar. That's what diabetes is. It's nothing to do with insulin. Or the resistance to insulin, so-called. There is nothing pathological about insulin per se, unless you inject artificially too much insulin from an exogenous source into a human being and don't counterbalance that with carbohydrate to prevent a rapid decline in the blood glucose, which would otherwise occur. Doesn't happen physiologically under any circumstances. You have to artificially induce that state of affairs. What are you talking about?
It's what you see in states where you basically can eat carbohydrate, but you can't effectively oxidize it.
Well, the situation there is very simple, isn't it? If you can't effectively, as you say, oxidize carbohydrate, it's because your cells do not require that carbohydrate to oxidize. They don't need it. They don't want it. They're being served perfectly well via energy from the source, the better source, the fat source. And as such, if glucose were allowed to flood into the cells according to the concentration gradient differential between the vast amount of glucose in the blood following a meal rich in carbohydrates, for example, that level of glucose inside a cell, in the cytosol of a cell, would ultimately be damaging to that cell and cause that cell to have a less useful lifespan, a shorter lifespan. It can cause all sorts of problems, basically. Glucose is incredibly toxic at a level above the physiological level. As such, the Randle cycle works in such a way, the analogy I always give, and I'll give it again here because it is still correct, is that the cell locks the door to sugar to protect itself from sugar, thus keeping the sugar outside the cell in the blood, where the red blood cells and the epithelial cells of the vascular tree become the sacrificial pawns, the sacrificial lambs. They suffer that damage, while ever the more important, more intricate cells of, say, the muscles and the organs and tissues and all that sort of stuff are absolutely protected by the effects of the Randle cycle in those locked doors, which I will cover in detail soon. That is why the Randle cycle exists, to protect cells from too much glucose flooding into the cell. The mechanisms, the kit, the machinery that causes that to occur is very clear and has been elucidated. Mike, the problem is you don't understand what it is, because your Wikipedia page couldn't point to it for you. And you are now reductively and reductionistly looking at an opinion statement put together by a couple of charlatans that only look at part of the picture and think you have the whole picture, when you don't, remotely. Okay?
Versus a non-pathologic or a
good stuff, isn't it?
Non-pathogenic insulin resistance. What's the word I'm looking for here? A physiologic insulin resistance. And
So what's the difference, Mike? How would you decide which is which?
In a physiologic insulin resistance, this occurs for example, in like a high-fat diet where you are indeed insulin resistant, but
No, you're not, because that's a construct. It's an idea. It's a fantasy. What piece of kit measures insulin resistance, Mike? What manufacturer makes an insulin resistance meter that I can purchase? Point me to it. Spoiler, it doesn't exist.
The function of not having adequate carbohydrate and having...
No, you always have adequate carbohydrate unless you are a type 1 diabetic with too much insulin on board. Okay, we've covered this.
A large amount of fatty acids flooding the system postprandially or after you're eating, and this essentially leads to excess fatty acid oxidation.
Excess fatty acid oxidation? No. The body will oxidize as much fatty acid as is required to subserve the needs of the cells for energy, with the proviso that such fatty acid is available to be oxidized, and with the proviso that it is not being inhibited in a meaningful way by the oxidation of glucose, i.e. the effects of the Randle cycle, Mike. There is no such thing as excess fatty acid oxidation. What a ridiculous comment. The exact amount that is required to be oxidized is oxidized in terms of the energy provision for a human being across time. Buffhead.
Blocks glucose oxidation. Now, in people who are doing high fat diets or keto diets or very low carbohydrate diets, when they add carbohydrate back in, they can then again become insulin resistant. It just
Number one, no, insulin resistance is a construct and a concept. And number two, why would they add carbohydrates back in? Carbohydrates are not required. They are contraindicated in the human diet. Carbohydrates are a subsistence means of survival in human beings for times when the hunt is unsuccessful or was unsuccessful in times gone by. Carbohydrates are not a preferred fuel source for human beings. They are damaging. They are toxic, absolutely without question. They are problematic. There is no indication that a single gram of carbohydrate should ever be consumed by human beings, ever. Not one.
takes a period of time. However, with diabetics or people with metabolic syndrome, what you wind up seeing is even if they have
Another construct, metabolic syndrome.
carbohydrate present, they still have insulin resistance. And there's a couple
No, they don't.
different things going on in these different states. There is some congruency between them. So there is some elements that are similar or some metabolic functions that are similar in both states.
What are you actually saying here, Michael? Anything at all? Anything? No.
But they're not exactly the same. There is a difference.
Well, what is it then? If you're saying there's a difference between useful so-called insulin resistance and unuseful so-called insulin resistance, tell us what it is. What's the difference exactly?
Now, that doesn't mean that over time...
No? We're just going to take your word for it, are we, Nursey? I can still hear those bedpans calling out to you, Michael, saying we haven't been cleaned yet, by the way.
An excess of fatty acid oxidation.
There is no such thing. There is no excess fatty acid oxidation. No.
Could lead to issues with glucose oxidation in the long run.
No. Glucose oxidation issues are reversible by basically draining the system of fats. However, should you do that? No, because a diet which is based on a large amount of carbohydrate with very little fats is a deficient diet in terms of micronutrient requirements. And macronutrient requirements too, to be fair. It is inappropriate. You cannot have your optimized health and longevity on a diet which is inappropriate for your speciation. Sorry about that.
Definitely possible. But in most situations that I think we'd be talking about with somebody who's on keto or carnivore, if they switch to a higher carb diet...
Why would they do that?
Appropriately, again, the key word here is appropriately.
There is no appropriate amount of carbohydrate in the human diet. It's all inappropriate, all of it.
Not the... I found the bioenergetic way of eating and I slammed a whole bunch of ice cream and orange juice and sugared milk and I gained a bunch of weight. I think there's a better way to introduce those things, but...
Why would you? There is no requirement for carbohydrates in the human diet. None.
When they do things appropriately, you're able to improve or recover that insulin sensitivity by minimizing an
Insulin sensitivity is just as much a construct as insulin resistance is. By the same argument exactly.
Excessive fatty acid oxidation. Also,
there is no such thing as an excess of fatty acid oxidation. Michael.
Again, I just want to point this out specifically. Stress states, being under large amounts of stress, triggers lipolysis.
And you've said that already, and it was irrelevant the first time, and it's still irrelevant to this discussion.
And gluconeogenesis and fatty acid oxidation through cortisol, adrenaline, glucagon, growth hormone.
So?
And in these situations, you have insulin resistance triggered by those.
No, you don't. It's a construct. Remember? Still.
The stress hormones.
What you have is an effect mediated by the machinery known collectively as the Randle Cycle, whereby if you have a rate of fat oxidation you will have a commensurate decrease in the rate of glucose oxidation, and vice versa. It's a counterbalancing thing. However, when you get one of those macronutrients in vastly higher amounts than the other, and in total there is more energy available than you are using per unit time, then the Randle cycle starts to get really kicked into its fully activated state, and you get complete blockade of things. That causes some knock-on effects, which I will refer to soon, which lead to the door locking mechanism, the very thing that the cycle is actually designed to achieve exactly. Okay? What's next?
You see the same thing in diabetes, and these same hormones are also strongly upregulated in keto and carnivore and other very low carb situations.
Gosh, really? The body responds to the energetic state that it finds itself in by releasing the right hormones in the right proportions to cause that body to maintain its homeostasis. Well, fuck me, Michael. That's incredible.
And even in fasting situations, even intermittent fasting, they're showing decreases in thyroid hormone, elevations in glucocorticoids chronically.
So fucking what? What's next?
Or over with chronic fasting, especially depending on how long those fasts are.
See, this is just noise, isn't it, boys and girls? You're not even talking about the Randle cycle. This is waffle.
Regulations of the catecholamines, upregulations of growth hormone. These are actually touted as benefits in the fasting communities, and then decreases in androgens and other sex steroids. So those hormones are elevating not because for example with the growth hormone in those situations is elevating not to like grow your tissues or help you lose weight.
Oh, get on with it, for Christ's sake.
It's increasing during fasting situations to help you oxidize the fatty acids better that you're liberating from your tissues.
Bugger me, the body responding in such a way as to optimize its functioning. Wow.
So it's not necessarily a good thing. You have to understand the concept.
It is for fuck's sake, Michael. Are you that stupid? Or do you just assume that your viewers have to be that stupid? They must be to believe anything that comes out of your ridiculous fucking mouth. Oh my God, this is pathetic.
Context of why these hormones are elevating. Anyway, I know I got off on a tangent. Let's
no shit.
Continue. Here, this is where we get specifically to the carbohydrate or fatty acid oxidation blocking carbohydrate.
No, inhibiting, not blocking.
Oxidation and what exactly the mechanisms are.
Well, it does block it at the 100% inhibition level and above, but that's only when you get to an extreme situation.
So I'm going to read through this section.
All right, you're going to be a scientist by reading through somebody else's opinion. You're going to convince us that you are a competent commentator on science by reading somebody else's opinion. Michael, good work, son.
This little pink area I'll read after. And then I'm going to go through the graphs. So I'll read through this.
This will be fun.
Just go through the graphs of things or the diagrams. And then
I've got some diagrams too to share with you.
I'll get to this section after to kind of cement the point home. And that'll wrap up.
No, reductively, in a reductionist fashion, that is, put forward your ideology, Michael, without reference to the objective reality and the holistic functioning of the human body whatsoever. As a complete charlatan and an incompetent of the highest order, that's what you're going to do.
Up the video for us today. So what they start here is they say, Randle, so this is Sir Philip Randle.
Yes.
Demonstrated that impairment of glucose metabolism by fatty...
See, impairment is another value judgment statement. It's not impairment because there is nothing deleterious about it. It's physiologically indicated. It's part of the homeostatic mechanisms of the human body. It's normal, it's natural, it's part of your holistic functioning. It doesn't, why would you refer to it as impairment unless you have an agenda to push? Which these authors clearly do by the fact that they have totally left out any discussion in their paper of the other side of the Randle cycle, which is true in parallel, simultaneously. That being, the fact that a large amount of glucose oxidation inhibits fatty acid oxidation as well.
fatty acid or ketone body oxidation was mediated by a short-term inhibition of several glycolytic steps, namely glucose transport and...
There you go, transport. The door locking mechanism, which you, Mike, claimed does not exist and has nothing to do with the Randle cycle. And yet, you've just read out a paragraph from a paper that you are now basing your video about how you know about the Randle cycle much better than I do, stating exactly that. Philip Randle understood. Even these two authors and their reductionist nonsense understood that Randle understood this. Why don't you understand it? The transport of glucose from the outside of the cell to the inside of the cell is inhibited when the Randle cycle is activated to any degree. Precisely and absolutely in order to protect that cell from the glycative damage it would otherwise suffer, were the glucose in high concentration in the blood allowed to just flood into the cell according to its concentration gradient. Thank you, Michael, for debunking yourself. Carry on.
Phosphorylation, 6-phosphofructose-1 kinase, so PFK1, and pyruvate dehydrogenase, so PDH. So the first one that fatty acid oxidation inhibits, well, it's not the first one, but the first one mentioned here is glucose transport and phosphorylation.
Yeah, that's the last thing that happens, glucose transport at the GLUT4 transporter up here. Okay. You will see that a buildup of citrate in the cytosol of this cell directly blockades the function of the GLUT4 transporter, which would otherwise bring the glucose into the cell. It locks the door. That's the door locking mechanism I'm talking about. Where does the citrate in the cell cytosol come from? It comes from citrate being generated in the mitochondria from an overspill from acetyl coenzyme A as being supplied in this case by the flow into the system of a lot of long-chain fatty acids at the CD36 transporter at the cell membrane. The transmutation of that into long-chain fatty acyl coenzyme A's, which are transported into the mitochondria by the CPT1 transporter, and then that long-chain acetyl coenzyme A undergoes beta oxidation, forming acetyl coenzyme A, and if it's not being used for oxidation, because there's no such thing as excess fatty acid oxidation, then the citrate builds up in the cell. Then it pours into the cell cytosol, thereby blockading the PFK1 and the PFK2 and the GLUT4 transporter. The doors are locked. No more glucose can flood into the cell and damage it. Thank you very much. I conclude my case. End of discussion. But you're not done yet, are you, Mike? So let's deal with the rest of your ridiculous, reductionist, charlatan, incompetent nonsense, shall we?
Into the cell. So when glucose gets to the cell, it gets converted to glucose 6-phosphate. This step gets impaired.
No, not impaired. Not impaired at all. Because it will start working again perfectly fine when the energetic state of the cell indicates that it's time for the cell to do that. As long as it does not require that energy influx or that pathway to be activated, and indeed it is indicated that that'd be blockaded because that would be damaging to the cell, that's what the cell does. That's not an impairment. That's normal, indicated physiological function. Okay? Idiot.
By fatty acid oxidation, but it's not the major area that gets impaired. The next,
there is no area that's impaired. Everything that happens here happens because there are enzymes working along this whole pathway, all of which are designed absolutely in terms of their amino acid makeup and the way they function by the instructions given by the genes, those genes having survived 13,800 million years of evolution at least, Michael. It's not an impairment, it's normal function. These things are doing what they should do for very good reason.
This one is 6-phosphofructose-1 kinase. So this is an enzyme in the glycolytic pathway, an enzyme in the process of glycolysis. So this gets blocked to some extent. But again, this isn't the major enzyme that gets blocked by fatty acid oxidation.
What do you mean the major enzyme? These things are all connected, end to tail, cause and effect. The fact that PFK1 is downregulated, the more fat that's being oxidized, up to a point where it gets to 100% inhibition, therefore is blockaded at that point, is indicated. What do you mean that's not major? That is a part of the cycle which prevents the cell from pouring a bunch of glucose into that cell that would damage it. Because the upstream effect of that is that there is also a blockade of the GLUT4 transporter directly by citrate. It blocks both of those things. My God, this is just unbelievable, the level of complete lack of understanding of the system that Michael has.
Now, pyruvate dehydrogenase is the major enzyme that...
Says who? Why would that be any more important? It's a part of a system of gears, if you like, all of those gears swinging off each other. You want to reductionistly look at what happens inside the mitochondria at the level of the pyruvate dehydrogenase complex, as if that's the only thing that's important here. You even said in your video the other day, Michael, that this other stuff up here, all of the stuff in the cytosol, was unimportant. You even denied its existence. You buffoon. Wow.
That gets blocked by fatty acid oxidation. And this enzyme is...
No, not blocked, inhibited until the point of blockade.
Extremely important because this is the enzyme that links glycolysis. So that's the process of taking glucose and creating 2-pyruvate to the Krebs cycle, where that pyruvate is converted to acetyl-CoA and eventually a citrate. And then from there, it runs through the Krebs cycle. You build up NADH.
No, Michael, citrate does not pour into the Krebs cycle. It's, my God. Wow. We'll cover that when you do the diagram on that in a bit. You don't even understand clearly the dynamics of the chemical equilibria involved here and the functioning of the enzymes. Wow. Wow. We'll get to that though.
And FADH2, which are electron carriers. They're the reduced forms of NAD plus and FAD respectively. So reduced meaning 2 electrons have been added, or not 2, but electrons have been added to them.
All of this is, well, it's interesting detail for those who are academically studying the underpinning mechanisms and workings of this. For a lay audience, Michael, this is all irrelevant and has nothing to do with the actual important physiological effects of the Randle cycle, which are up here at the top of this graph here. When you have a lot of fat pouring into the cell, this means that the acetyl coenzyme A delivery is adequate, and as such, sugar is not required. Ergo, the pyruvate dehydrogenase complex is downwardly inhibited. The entry of pyruvate is therefore downward inhibited directly. While ever we're at it, if there's more than enough acetyl coenzyme A, then the citrate will start to leach into the cell cytosol, and that will directly blockade those enzymes and prevent the cell from being poisoned by too much sugar by, to use the appropriate analogy, locking the fucking door. Okay? That's the important mechanism. That's what you need to understand. The cell is protecting itself. Of course it is. All right? Goodness me. Goodness gracious me, what's next?
Those electrons have a negative charge, which is why they're called reduced. And then essentially those get moved to the electron transport chain,
Again, interesting, but irrelevant.
When they're moved to the electron transport chain, they move through the electron transport chain enzymes. The enzymes pull the electron.
Now you want to give us a lecture on the electron transport chain, which is not really anything to do with the Randle cycle and its meaningful physiological effects. It's an irrelevancy, really, and it's a level of detail that is not required for the lay audience, Michael.
Electrons off those carriers, and in doing so, pump protons or H plus ions in.
No. No. Again, learn some basic chemistry, Michael. That is wrong. It's the way it's typically described, but it's a parsimonious description which is incorrect in fact. A competent chemist understands that.
Into the inner mitochondrial space, which creates a gradient, and then that gradient of protons runs through an enzyme called ATPase, and it's like
ATPase, not ATPase.
Kind of like a hydroelectric dam.
It's an A's that's involved in the production of ATPs. Therefore, it's an ATPase, not an ATPase. For goodness sake.
And then it produces ATP. And I'm going to go over all of this in just a second. So if everything I just, like with a graphic, so if everything I just said sounded like a whole bunch of non-English.
It's irrelevant. It's technical information for those who are studying the actual underpinnings, the cogs in this gearbox. The lay public don't need to know this, Michael. It's irrelevant.
Or just like gibberish to anybody, then don't worry, I will show you exactly what I mean. But the main thing to keep in mind here is that PDH, pyruvate dehydrogenase, is the main enzyme.
No, it's an enzyme. Well, it's not even an enzyme, Michael. It's a complex of a bunch of enzymes.
That gets blocked.
No. Not until the point of complete inhibition. Before that, remember, it is inhibited, not blocked.
By fatty acid oxidation,
No.
fructose kinase, and the glucose transport and phosphorylation. Both of those are secondary to PDH. PDH.
Yes, they're an effect. They're a flow back effect, but they are not secondary importance. They are the point. That's why it occurs, Michael, to protect the cell. For goodness sake.
H is really the main one.
It's not the main one at all. It's where the effect begins. Its effect is downstream by flowing back upstream, if that makes sense.
So what they say is the extent of inhibition is graded and increases along the glycolytic pathway.
Yes.
Being most severe at the level of PDH and less severe at the level of glucose uptake.
Depending on how much fatty acid is pouring through. It gets to a point where there is a complete blockade. In very extreme situations, a complete blockade can occur, momentarily or for a period of time, according to the energetic state of that cell, Michael.
Glucose uptake and phosphofructose kinase. So this is exactly what you're saying. Pyruvate dehydrogenase is the main enzyme that gets blocked.
No, it's not. You're saying that. They haven't said that in this paper. Philip Randle never said that. That's what you're saying. That's your interpretation. Remember, I thought this thing wasn't open to interpretation. Well, you've just interpreted it, Mike, and you've got it completely fucking wrong. Because of your incompetence. Your complete incompetence to talk with any degree of authority on this topic. Okay?
This sequence occurs because the initial event triggered by fatty acid oxidation is an increase in the mitochondrial ratios of acetyl-CoA to CoA.
Yep. Down here. Absolutely. Fat pours in. Coenzyme A, acetyl-coenzyme A, starts to build up. If the rate of acetyl-coenzyme A in the mitochondria runs to the point where you have a higher concentration there than is required, according to the energetic requirements of that cell oxidation at that time. Or indeed, if there's any significant amount of acetyl-coenzyme A being thrown in from the other direction from pyruvate dehydrogenase complex, Michael. Okay? Really easy to understand.
And NADH to NAD plus. So you have get a buildup of these reduced carriers. This is what Dr. Pete is talking about when he talks about reductive stress. So you're seeing
That's also a construct and a concept, and it's fucking ridiculous, Mike. It's not based in science. It's a fantasy world put together by a fantasist. Ray Peat is a fantasist. Okay? The changing ratios of NAD to FAD, both oxidized and reduced forms of those cofactors, is another form of signaling. It's another way that the mitochondria understands the energetic state of what's going on around it, and as such, it communicates that back to the cell at large in order to protect that cell from damage. It's a relationship, a codependent relationship that has developed over billions and billions and billions of years, and it works really effectively. Also, the mere assumption that stress is inherently a bad thing is false, Michael. Zero stress means you're dead. A level of stress is indicated, and it's informatory. Okay? Your total lack of understanding of everything here, Michael, is just beyond belief. As is your stunning arrogance and Dunning Kruger thinking yourself competent to comment sensibly on something on the basis of reading somebody else's arrogant, stupid opinion. Wow.
a buildup of this NADH in ratio to NAD, and we'll see why that's important in just a second. Excuse me. So, and again,
it's almost like you've got some gastric distress going on there, Mike, for some reason. I wonder what that might be.
And both of the excess acetyl-CoA in ratio to CoA and an excess of NADH in ratio to NAD+.
Again, excess would seem to be a value judgment statement. Is this not a useful, meaningful message? A feedback loop? Perhaps it is. Ever think of that? Ever think at all?
Both inhibit pyruvate dehydrogenase activity. So this,
for a reason. Yes.
These are some of the main mechanisms. There's other that we'll talk about here.
What is that reason? Well, the reason is to cause that energy to flow back upstream to a point where that door is locked and no more sugar can enter the cell because it would be poisonous for it to do so. Because the cell has enough energy. Thank you very much. It does not need any further input from sugar, and a buildup of sugar would be toxic. Okay? Straightforward, really.
Then they say it has been proposed that these changes lead to an accumulation of cytosolic citrate, which in turn inhibits.
Yep, there it is there.
Inhibits phosphofructose kinase, followed by an increase in glucose 6-phosphate, which eventually inhibits hexokinase. So hexokinase is that enzyme that takes the glucose, helps to create glucose 6-phosphate and bring that glucose into the cell. However, a buildup of glucose 6-phosphate, basically a buildup of the product of this reaction, inhibits the reaction to some extent. So, and
right, for good reason, as we can see on the chart. What's next?
And again, they talk a little bit about this in more detail, but this is not as important as pyruvate dehydrogenase. And
yes, it is. It's the point. It's the whole fucking point. My God. Idiot. Your interpretation is so stupid, it's unbelievable.
And citrate, which is a mediator, it's a mediator, a metabolic intermediate in the Krebs cycle, inhibits phosphofructose kinase 1. And so the inhibition, so the citrate builds up because of the...
It's almost like it's a negative feedback loop, which has evolved over 13.8 billion years, I should say, precisely in order to protect the cell from damage. All of these things working together synergistically to achieve the same end. Goodness me.
Poor activity of PDH in the Krebs cycle.
Well, it's not poor. It's indicated if it's limited, downregulated, blockaded even, when the energy is not required from that pathway. It's like turning the light off in a room that you're walking out of and you don't need light in anymore because you're no longer there. Don't waste the electricity. Turn the light off. And actually, it's even more important than that because the energy flowing into that room when you're not in there, in the form of sugar, not using it, damaging, toxic. It has to be blockaded. Ergo, the means to blockade it has evolved, and this is what it is. Fuck me, this is really easy to understand.
And then that buildup of, and again, that the poor activity of PDH in the Krebs cycle.
It's not poor. Not poor at all. It's inhibited because it's supposed to be inhibited.
Happens because of some issues with the buildup of NADH and acetyl-CoA. And in a sense,
they're not issues. They are messengers that elicit and cause that event to occur because that event is indicated and utilitarian.
Essentially, what you wind up see happening is the citrate basically goes onto the phosphofructose kinase 1 enzyme and impairs its function.
It not impairs, downregulates it because it is supposed to. The PFK binds to the citrate precisely because it has evolved to do so in this circumstance, precisely to achieve the effect that that achieves. The downregulation of the activity of that enzyme. Fuck.
So this is a specific mechanism where the buildup of citrate is impairing this particular enzyme here.
Not impairing it. No. Impairment denotes a problem. This is not a problem. This is not pathological. This is indicated and required to protect the cell from damage.
And again, phosphofructose kinase 1 and glucose and a hexokinase or a buildup of glucose 6-phosphate aren't the main problems with fatty acid oxidation blocking carb oxidation.
There are no problems with fatty acid oxidation blocking carb oxidation. It is indicated. The problem is in continuing to pour contraindicated unnecessary carbohydrates down your stupid neck every day of your stupid life, thus causing the blood sugar to raise ever more and ever more and ever more, because your body will not use that in your cells, because those cells are protecting themselves from that damage that they would otherwise suffer by allowing that sugar to just pour in there. Man, this is really not rocket science.
It's really that blockage at pyruvate dehydrogenase. So
that's what initiates the cascade, yes. That doesn't make it the main thing. It makes it the first thing that occurs. The other events occur through the flow back of that energy through that pathway, as they are supposed to do. The main point being the end point, which is the blockade of sugar entering the cell when it's contraindicated and unnecessary. Okay?
So, and again, I'm going to show you this. I'm going to show you guys this whole path.
He's going to show us guys all of this is
pathway in just a second,
which is going to be irrelevant and pointless to anyone except those who want to academically study in huge detail the minutiae of the actual workings of the system, which you shouldn't get from Mike anyway, because he can't even interpret what the meaning of the thing is.
There's more blocks on the pyruvate dehydrogenase enzyme, and that
it's not an enzyme. It's a complex of a number of enzymes, you buffoon.
And we're going to get into that right now. So what they say is the products of PDH exert a feedback inhibition on its activity.
Yes.
So the product of PDH is acetyl-CoA.
Yes, and a few other things as well.
And essentially what happens is when that builds up and inhibits PDH's ability to produce more acetyl-CoA. So,
Jesus, it's almost as if what that means is that when there's enough acetyl-coenzyme A and citrate is starting to build up and pour out into the cell, that the cell inherently knows that we have enough energy coming in here. We don't need to continue to use this pyruvate energy, so let's blockade that mechanism so that that energy all backlogs up the system to the point where that cell then locks the door and protects itself. Oh yes, that's right. That is what happens. Okay, what's next?
So it has an inhibitory effect on PDH. And this is, in chemistry, this is kind of known, I think it's Le Chatelier's principle, where a buildup of the product of a metabolic reaction can inhibit the reaction to some extent, or push...
Not can, it does.
The reaction in the other direction if it is reversible. And there's a couple reasons for why, but essentially the buildup of...
Well, it's basic physics. It occurs necessarily via the anthropic principle because it could be no other way.
The products of pyruvate dehydrogenase block its activity.
You've said that already. We understand, and it's indicated.
So if you build up of that, the enzyme stops functioning as well.
Yeah, you've said that. We get it.
In conjunction with a buildup of the acetyl-CoA NADH, which is actually part of this mechanism anyway.
Yes, fine, whatever.
What they also talk about here is dedicated mitochondrial kinases, pyruvate dehydrogenase kinase, phosphorylate, and inactivate pyruvate dehydrogenase, whereas pyruvate dehydrogenase phosphatases have the opposite effect. Control of pyruvate dehydrogenase activity.
Yes, these are the mechanisms by which the enzymes can be up and down regulated in their activities within a working cell. So what, Michael?
Depends on the relative activities of PDK and PDP.
Yes, so what?
And on the extent of phosphorylation of the E1 subunit sites. So PDK is the pyruvate dehydrogenase kinase, and PDP is the pyruvate dehydrogenase phosphatase.
Yep.
Now, phosphatases increase pyruvate dehydrogenase activity, whereas kinases decrease pyruvate dehydrogenase activity. So if you have an upregulation of pyruvate...
We understand, for God's sake, we get it, but it's irrelevant. It's just the mechanism by which this occurs. So what?
Pyruvate dehydrogenase kinases, then pyruvate dehydrogenase gets shut down, essentially. And that impairs the flow of carbohydrate from the glycolysis.
No, not impairs. No, downregulates in an indicated fashion.
Into the Krebs cycle. And then if you have increased activity of pyruvate dehydrogenase phosphatase, then you will increase pyruvate dehydrogenase activity. Also, if pyruvate dehydrogenase kinase activity gets downregulated, then pyruvate dehydrogenase activity.
Right, so through a bunch of negative feedback loops and positive feedback loops, the human body, the human metabolic system has a way of upregulating and downregulating the activity of various enzymes precisely in order to maintain one's homeostasis and protect the cell from damage. Okay, great. Thanks, Mike. We get it.
Can increase. So though all of those mechanisms are at play, and that'll become important as we talk here. So what they say is pyruvate dehydrogenase substrates and products also control pyruvate dehydrogenase kinase activity.
Yes, of course they do.
Pyruvate, or its analog dichloroacetate, inhibits, whereas acetyl-CoA and NADH stimulate pyruvate dehydrogenase kinase with isoform-specific differences in sensitivity. So depending on the type of pyruvate dehydrogenase, the isoform, the different type of enzyme, some are more sensitive than others to these products.
Yeah, so
acetyl-CoA or NADH or pyruvate or a similar compound to pyruvate dichloroacetate in terms of their inhibition or accentuating effects. Or activating effects, I guess would be a better word. But the real thing to keep in mind is that a buildup of acetyl-CoA and NADH increase PDK, which further shuts down pyruvate dehydrogenase.
Yes, because it's supposed to.
While acetyl-CoA buildup and NADH all in and of themselves also shut down pyruvate dehydrogenase. So you have multiple mechanisms here shutting down pyruvate dehydrogenase.
It's almost as if that's supposed to happen, Michael.
Activity with a buildup of NADH and acetyl-CoA. And this is going to be really important when we go through the graphs, and I'll explain all.
No, it isn't. It's going to be irrelevant.
All of that. The last thing I just wanted to read here is inhibition of glycolysis. So pyruvate dehydrogenase is the enzyme that links glycolysis to the Krebs cycle.
Yeah, you said that before already. We understand.
So that's the main block, that linkage.
No, it's not the main block at all. No, you've got that wrong again. Still.
Enzyme.
It's the starting point of a series of reactions that are all geared towards an outcome, but it's not the main anything.
But pyruvate, the glycolysis, as I discussed before, also gets inhibited, but the inhibition is smaller compared to the inhibition at pyruvate dehydrogenase.
So the magnitude of the effect at various stages of the metabolic machinery are all geared around the functioning of that bit of machinery, that being up here at GLUT4. And here at PFK1, and in effect here at PFK2, and therefore at fructose 1,6-biphosphate, etc. Everything is geared to produce the exact result at the exact magnitude which is physiologically indicated, and all of that occurs because of 13,800 million years of evolution, Michael. Okay?
Fatty acid oxidation doesn't really shut down glycolysis as much as it shuts down glucose oxidation or through the Krebs cycle.
And that would make sense, wouldn't it? Because what is it that's required absolutely at all times to fire all muscle contractions in all muscle cells, for example? Oh, yes. Glycogenolysis, actually, in fact, but that's for another day. So we wouldn't want to inhibit that. So therefore it's not. Okay? Again, it's almost as if the human body has organised itself according to the anthropic principle over a period of 13,800 million years to work the way it should, pretty much. If we would just get out of the way of the human body, if we just get out of our own stupid way and live our lives the way that as nature intended us to do, i.e. eat a species-appropriate, species-specific diet and lead a species-appropriate, species-specific lifestyle, that we'd have the best chance of the most robust health for the longest period of time each as an individual. Look at me, there's a thought.
And so what they're just saying is there's about a 20 to 30% decreased uptake for glucose due to an increase in fatty acid oxidation.
So
this would be at
That's exactly the level it should be at.
Kinase, and then there's a 40 to 60% decreased flux through phosphofructose kinase 1.
Well, hang on, that's a higher level of inhibition than that at the PDH, isn't it? Can you see how 40 to 60% is more than 20 to 30%? See, the inhibition is relatively small for glucose uptake and 40 to 60% for the PFK1 flux. Anyway, it doesn't matter. It's all geared around the exact levels that it should be to achieve the end result as it should be.
So that's the flux, I think it's of glucose 6-phosphate through this enzyme to create, I forget the other product that it creates in the glycolytic pathway, but it basically will block this enzyme or decrease the flux of the product of the substrate through the enzyme by 40 to 60%. And decrease that glucose uptake specifically by 20 to 30%. And again, and this is compared with almost complete inhibition of pyruvate dehydrogenase. And then it says, as initially proposed, phosphofructose kinase 1 inhibition results from the accumulation of citrate, a well-known allosteric inhibitor of phosphofructose kinase 1 and phosphofructose kinase 2, as later demonstrated in liver and heart. So an allosteric modulator, I know it sounds like a fancy word, but
no, not really.
Essentially, it's when something binds onto an enzyme, or perhaps, yeah.
You've already explained this.
It binds onto an enzyme and basically impairs that enzyme's ability to
No, not impairs. No, impair is a value judgment statement.
Undergo its reaction. So the way I guess you could think of it is like if the enzyme is this like crystalline structure or like a series of magnets, like a ball of magnets.
It's not though. I thought analogies were bad, Michael, and sloppy. It's nothing of the sort. It's a bunch of amino acids put together in a certain sequence, which then fold up in a certain way to make a certain shape that initiates a certain or reduces the activation energy of a certain reaction, thus making it easier for that reaction to occur.
Magnets with different interactions amongst each other, and that's giving it its shape, kind of like if you had like those magnetized marbles and you throw them on the floor, they'll all
it's nothing like that at all.
Interact to create this shape. If I put a super strong magnet on one side, it changes the shape of those magnets, and now if there was a little
it doesn't
pocket in those magnets that was supposed to bind the glucose 6-phosphate, the glucose 6-phosphate doesn't fit so well anymore because
this is all completely irrelevant to the point, isn't it? All you need to say for a lay audience, Michael, is that the phosphofructokinase enzyme is allosterically inhibited, which you can explain as the binding of the citrate to the PFK1 to change its conformational presentation in such a way as to downwardly activate its activity. Fine, let's move on. We don't need this level of detail. It's irrelevant to your argument, which is fucking stupid, by the way, remember?
The citrate, in this case, that bound onto the phosphofructose kinase changed that pocket shape, and now the molecule of the glucose 6-phosphate essentially doesn't fit as well, so the reaction doesn't occur as as nicely or as strongly or as good as we want it to.
No, it occurs exactly because it is supposed to occur, and it thus downregulates the effect of that enzyme so that it does exactly what we want it to do. Idiot.
So that's essentially what an allosteric modulator is. It's just something that binds to an enzyme and impairs its function.
You've said that. We understand. Even those of us who are very, very limited understand that.
I know it has a fancy name, but that's basically what goes on.
Wow, you are the worst presenter I have come across in a long time, Michael. You really are. You need to write yourself a script clearly and stick to it.
So now, basically, we've gone through, this is the meat of the article. I'm not going to go too...
Right, so you've completely, utterly ignored this chart. Which is simultaneously true to the chart we've been looking at, and is also affected by the machinery known as the Randle Cycle. A bunch of glucose gets transported into a cell via the GLUT4 transporter, which runs through the PFK1, PFK2 system so that we get fructose 1,6-biphosphate, which then is transmuted to pyruvate, which goes through the pyruvate dehydrogenase complex and produces acetyl coenzyme A, to a point where citrate starts to pull in exactly the same way as it did when the energy was being provided from the fats, largely. It then pulls into the cytosol in exactly the same fashion. Then there's an enzyme called ACL, which produces acetyl coenzyme A in the cell. That is then through another enzyme called ACC, which produces a thing called malonyl coenzyme A, which downregulates the CPT1 and the CD36 directly, thus blockading the fat. It's almost as if the cell's saying, I've got enough energy at the moment coming in the form of acetyl coenzyme A is sourced through the glycolytic side of the equation, and as such we can go into fat storage mode, and we're blockading the import of fats for fat oxidation, and we're now building up fat molecules instead. One of the reasons why you shouldn't base your diet on carbohydrates, because it will put you into a fat storage mode. There it is, right there. Interesting, isn't it? Of course, if the citrate continues to pull because there's too much glucose, then what happens? This does, doesn't it? Because it's simultaneously true. It's almost like the cell is energetically controlling the amount of stuff that's coming in here, and what gets blockaded? Well, if there is sufficient energy coming into the cell in the form of fat, then sugar will be, for want of a better term, inhibited or blockaded, depending on the level of fat coming in. If there is enough energy coming in the form of carbohydrates, there's a limit placed on that too, by the exact same piece of machinery. Look at me, 13.8 thousand million years of evolution has this sorted out. It does exactly what it should do and exactly the way it should do it. Incredible. What's next?
Much more, because it gets into like PPARs and genetic control of these different things. I really just wanted to talk, and that's separate from the Randle cycle. I wanted to just talk about the Randle cycle, but
you didn't though, Michael. You talked reductively about some of the aspects of the Randle cycle and forgot completely the rest. And you downplayed the importance of the whole point of the thing, which was to protect the cells from glucose. Idiot.
I want to describe the process for you guys here.
Okay, so now he's going to talk about the TCA cycle, otherwise known as the tricarboxylic acid cycle, otherwise known as the citric acid cycle, otherwise known as the Krebs cycle. This is irrelevant. to anybody except those who are academically interested in the workings of the Krebs cycle, which works exactly the same way, irrespective, actually, of whether the input of energy is in the form of fats or carbohydrates. Pretty much.
So what I was describing earlier is, I don't have glycolysis pictured, but with glycolysis, you have one molecule of glucose creates 2 molecules of pyruvate.
Yep, so?
And then you have the enzyme. I don't know if you guys can see it here. This is, let me see. So there's pyruvate dehydrogenase.
Which again, you are inaccurately describing as an enzyme. It's nothing of the sort. It's a complex of enzymes.
You can see that there. The pyruvate dehydrogenase is the enzyme that takes the...
No, it isn't. It's a complex.
Pyruvate from glycolysis.
See, you want to tell us all about biochemistry, son, and you don't even know that.
And turns it into acetyl-CoA. And by turning it into acetyl-CoA, it gets... Eventually, there's another reaction with citrate synthase where citrate is created.
Right. So citrate up to a certain level, thus building up in the cell, will drive the citric acid cycle ever more rapidly up to its maximum capacity. After which, we exceed that maximum capacity or cycle rate, if you like, and then the citrate starts to pool. Here and here. So, why do we need to spend any amount of time talking about the TCA cycle here, Michael? That's at a level that's completely unnecessary for this audience.
From oxaloacetate and then the acetyl-CoA. So this is a cycle that continues to spin, and then feeding glucose in the cycle that in the form of 2-pyruvate allows the cycle to occur.
Yeah, but also if you feed fattin in the form of acetyl coenzyme A, it does exactly the same thing.
Fatty acids can also enter into the Krebs cycle through acetyl-CoA. I'm pretty sure it's acetyl-CoA, yeah.
There you go. You're not even certain of that. Wow. Wow. Yes, Michael. Acetyl coenzyme A is the thing fed into the Krebs cycle from beta oxidation. Yes, it is. Good work, son.
So then, and that allows the energy production to occur. Now,
right. So what's your fucking problem?
Now, what you'll see here, and now the one thing that's not pictured is the FAD and
Yeah, so what?
FADH2, but it's similar to, if you guys see here, there's NAD plus and NADH. So what you're seeing when you see these little arrows coming off is NAD gets fed into this reaction of isocitrate dehydrogenase. So you get isocitrate plus NAD plus, moves to the enzyme isocitrate dehydrogenase and forms NADH and an H plus ion. Otherwise,
no, wrong. It's typically described that way parsimoniously, but it's factually incorrect.
Is known as a proton. So these enzymes are producing the NADH.
Protons exist free only in the form of plasma at very, very high temperatures and energy levels. Okay?
Also around here, around the succinate dehydrogenase.
But where exactly, Michael? You're the expert here, remember? So where exactly does FADH act?
Production of...
See, you're waving around here somewhere. Well, where exactly?
FADH2. I'm pretty sure it happens around...
There you go. See, now you want to present yourself as the expert here. You're not even sure whether acetyl coenzyme A from beta oxidation is the same thing as acetyl coenzyme A from pyruvate dehydrogenase complex. It is. And now you're telling us that FADH is so very important here to what we need to understand, but you don't know exactly where it acts. Okay, Mr. Expert, carry on.
Succinate dehydrogenase. So succinate plus its FAD moves through succinic dehydrogenase or succinate dehydrogenase and then produces the FADH2 amongst other components. I don't memorize them off the top of my head.
Great. You're an expert, clearly.
But essentially, this is really important to understand because...
Yes, it would be. If you did, Michael.
When you have carbohydrates, you get a higher production or a higher ratio production of NADH
Yes.
to FADH2.
Yes. So what?
So the carbohydrates produce more NADH in ratio to FADH2 than fats do.
So?
Fats produce comparatively to carbohydrate more FADH in ratio to NADH.
Really? We couldn't work out for ourselves that follows from what you just said. And so?
And this will become a really important process as we discuss later.
No, it won't.
When I go through as you can see behind here, there's the little the electron transport chain. But essentially, those electron carriers are very important. So in the process,
yes, but so what? And in what way are they important, Michael?
Of beta oxidation, where you're basically harvesting the fatty acids and the carbons off the fatty acids and their bonds to create these electron carriers in the form of NADH and
No, that's not what happens, Michael. No, you haven't even got that right.
FADH2, you get, comparatively to carbs, more of that FADH2.
Yes, you've said that already. We've got it. We understand. But so?
And NADH. And then with carbohydrates, you have glycolysis, and then they also move through the Krebs cycle. You'll get, comparatively to fats, more NADH.
Yes, you've said that. We understand. So?
Then FADH2. I'm not going to go through exactly why that happens now. Perhaps I'll make a video on showing the actual...
Oh, Jesus Christ, really?
...breakdown and the count and the ratios of FADH2 and NADH2 between beta oxidation and glucose oxidation. But just right now, all you need to know is that the ratio is higher with fatty acids.
We get it. You've said that. I don't know how many times already. It is still irrelevant.
Acids of FADH2 to NADH compared to carbohydrate. And that becomes extremely important when we go to the electron transport chain, which
no, it doesn't.
We're going to go to in a second. Now, the only other thing I want to share with you here, just to keep in mind, is that in the Krebs cycle, if you notice, in order for this reaction to occur through isocitrate dehydrogenase or pyruvate dehydrogenase or alpha ketoglutarate dehydrogenase or malate dehydrogenase, you need NAD. You need NAD.
Yes. That's why it's always there. That's why it's always there. Fuck, the echo's good in here, isn't it? Fuck, the echo's good in here, isn't it?
So you need, for example, if you want to create alpha ketoglutarate, you need deisocitrate and NAD.
Yes, we understand. We get that. That's why it's always there.
For this reaction to occur.
Yes.
If you don't have NAD, this reaction cannot occur because...
And therefore you die very quickly. That's why it does not occur, Michael.
You don't have the precursors for it to occur. Same thing with pyruvate dehydrogenase, specifically pyruvate dehydrogenase, and we'll get here in a sec. So just keep...
Well, hang on. I thought we've already spent more than enough time on pyruvate dehydrogenase complex, which you've finally described as a complex. Why do you want to go back there again?
Keep that in mind. You need NAD.
Yeah, we get it. That's why it's always there.
You also need FAD. It's just not pictured here.
Yes, we understand. What's next?
So now let's go over to the electron transport chain. Here we have the electron transport chain.
Well, it's a diagrammatic representation, sure.
You can see, let me just move it up a little bit. Here you have the lipid bilayer. So this is the phosphate head with the fatty acid tails. Then you have the intermembrane proteins. These are the complexes: complex 1, complex 2, complex 3, complex 4. They're, I know it's very creative names for them. Other thing I want to point out here is you have coenzyme Q, and this is extremely important. We're going to...
Yes, coenzyme Q10, in fact, otherwise known as ubiquinol. It's a substance that's very, very important in energetics. It's also downregulated, by the way, in its expression when you take statin medications, for example. It's a dangerous, contraindicated metabolic poison for that very reason, right there.
To talk about it in a second. So essentially what happens at the electron transport chain, these carriers that we produce in the Krebs cycle, NADH and FADH2, and the reason I call them carriers again is because they're holding electrons. So NAD plus can accept 2 electrons, then it becomes NAD.
Oh, for fuck's sake, really? It's like watching fucking grass grow, Michael, honestly.
D without the plus because the electron's negative, and the negative electron cancels the positive charge of the NAD, and then it gains another electron, which makes it NAD minus, which allows it to hold a hydrogen ion or proton.
No.
Because the proton is positively charged. So now you have NADH, which has a neutral charge because the electrons and the protons are canceling each other out. And the same thing happens with FADH2. So you have FAD, it gains 2 electrons, and then it can hold 2 protons. So that's why you have FADH2. Now the electrons from NADH and FADH2 move to their respective complexes here. So NADH drops 2 electrons off at complex 1. And FADH2 drops 2 electrons off at complex 2.
Yes. So what?
Now, in order for these electrons move to different enzymes, and as they move to these different enzymes, they pump these H plus ions across the membrane. So
well, no, because they're not H pluses.
So the enzymes use the energy from the electrons, kind of like, little pumps, and they pump these H plus ions that you can see right here into the inner membrane space of the mitochondria. And what happens is there's less H plus ions here, and there's more H plus ions over here, kind of like a battery. Now, essentially what you see, there's another enzyme that's not listed here. It's called ATPase.
ATPase, the H0H1 ATPase subunits, not ATPase.
And you can think of it like a hydroelectric dam, like a water wheel.
No, analogies are bad, remember, Michael. We mustn't use analogies at all. We mustn't say doors when we're talking about protein transporters on the cellular membrane, because that's bad. So no, we don't use analogies, remember, Mike, you fucking hypocrite.
And as these H plus ions come...
We also don't refer to physical things as bits of kit or machinery, unless it suits us to do so in our own video, which you've done, Michael, you fucking idiot.
Through, and they move down through the enzyme. You can literally say this isn't ATPase, but say this was ATPase.
It's not an ATPase, so why say it is one?
They just move down through ATPase here.
ATPase.
And as they turn that little water wheel, you get...
It's not a water wheel at all, no.
ATP is created. I guess it's the most simple way to think of it. Now, there's a little... essentially...
Irrelevant, Michael, all of this.
Actually, what you're seeing is that the electrons are powering these complexes, but they're moving from complex to complex. So the electrons at complex 1 go to coenzyme Q, which carries them to complex 3.
Yes.
The electrons at complex 2 go to coenzyme Q, which carries them to complex 3.
Yes.
Those electrons can move through cytochrome C.
Not can, do.
And then to complex 4.
Yes.
Now, you have a little... There's a nuance here. There's a caveat. And some of you may have caught it. Complex 1 and complex 2 both share coenzyme Q.
Yes. So?
This is a big deal because
No, it isn't.
If you have a lot of FADH2 here, complex 2 starts to hog coenzyme Q.
Not really, no. Because for that to occur, you would relatively have less NADH, wouldn't you? Because you're talking about the ratios. And as such, the exact same amount of effective energy is being transferred from complex 1 and 2, in effect, to complex 3. No harm, no foul.
So the electrons are going to complex 2 and then coenzyme Q, and complex 2 and then coenzyme Q. So what winds up happening is NADH can drop its electrons off at complex 1, but there's nowhere else for them to go.
The same is true of the electrons provided to the electron transport chain by FADH2. They just go to different complexes, either 1 or 2. In either case, it is coenzyme Q10 that transfers that energy to complex 3. So what?
So complex 1 starts to get jammed up.
No, it doesn't, because remember, the thing that... Jesus Christ, this is not hard to understand. There is more FADH2 and less NADH.
And what happens from the complex 1? You start to see a large production of reactive oxygen species from...
Got a research article that shows that to be the case?
From these electrons with nowhere to go, nothing to do. The other thing that
doesn't happen, Michael,
happens is when you get jammed up here, NADH cannot unload the electrons to complex 1, and so you start getting a backlog of NADH.
No, because remember the thing that led to a higher relative amount of FADH2 was a lower amount of NADH? Remember that? So no, it's not a problem.
So if you have...
It's part of normal functioning.
Too much FADH2 and...
No, too much FADH2. Again, a value judgment statement based around no science of any kind. No. Wrong.
Ratio to NADH, which is what happens again with fatty
ratio.
acid oxidation. With beta oxidation, you get more FADH.
Yes, we understand that, and it's not a problem. The body is designed absolutely through both positive and negative selection pressures to run on fatty acid oxidation primarily, and it's evolved over 4.5 million years at least.
To compare in ratio to NADH comparatively to carbohydrate, what winds up happening with that change in ratio, it leads to excess FADH2.
No, it doesn't.
At complex 2, which
no, it doesn't.
Basically hogs coenzyme Q.
Nonsense.
Creates this backlog and issue at complex 1.
Nonsense. It does no such thing.
Where you build up NADH and you
don't
produce ROS. Now,
reactive oxygen species are produced by mitochondria at all times at various different levels, depending on the energetic state of that mitochondria at that time in that cell based on what's going on. So what? It has means to deal with the reactive oxygen species being produced, like dismutases and uncoupling proteins, Michael. What's your problem?
The ROS can be a problem because yeah,
and it cannot be a problem too.
ROS can damage this membrane.
That's why we have reductases, dismutases, uncoupling proteins to protect the cell from that damage. It's almost as if the cell's been doing this for a very, very long time and has worked out a way of doing this in a way that's the least problematic and damaging to itself. Goodness me. Oh, yes, it has.
Can damage the proteins, can damage the mitochondrial DNA, etc.
That's the great thing about the word can. It leaves the other thing entirely on the table. Maybe it doesn't too.
So what happens? Now, it depends on how much ROS is generated, but an uncoupling protein can...
There you go. Thank you very much. End of your own stupid... You've just eviscerated yourself again there, Michael. You absolute fucking buffoon.
Come to the membrane, and the theoretical basis essentially will basically... dissipate the H plus ions in the form of heat. So
this is like a first year student giving a presentation to a class in a very unorganized fashion in terms of the comprehension of the material at hand. This is the kind of presentation I'd probably give a C- at best to, Michael. You'd be lucky to pass because you've shown absolutely no ability to interpret the physiological meaning of any of the stuff. You have shown only that you are able to read a paper written by some idiots, reductionists and charlatans, and yourself be an idiot reductionist charlatan, and point to a bunch of things that you've read about stuff in a reductionist way without actually looking at its functioning in any way, shape or form.
Another protein gets put in the membrane. It's called an uncoupling protein. The reason it's called uncoupling is because it uncouples the electron transport
fuck me, really. Thanks, Michael.
chain from the Krebs cycle in the sense of producing energy in the form of ATP. What winds up happening is it just increases heat production. So the uncoupling protein comes to the membrane here. It basically eliminates this H plus ion.
Right, so the problem that you're talking about occurring doesn't occur then because of the fact that the cell has mechanisms to prevent that from happening. Well, bugger me. Okay, what's next?
Gradient, and basically helps to minimize the ROS production.
Right, good. Okay, can we move on then?
Now, what winds up happening is you...
Remember this was about the Krebs cycle, not the Krebs cycle, it was supposed to be about the Randle cycle. Remember that, Michael? And you talked about a small amount of the Randle cycle, what happens at the pyruvate dehydrogenase complex a little bit. You downplayed the importance of the actual point, which was everything in these red enzymes are here on the chart at the top, even though they're actually the point. They're the reason the whole thing exists. They're why it does what it does. You've indicated that all of this is the main point when it's nothing of the sort. And now you're talking about a whole bunch of stuff that's happening here in the electron transport chain, which is totally and utterly irrelevant because it happens either way, whether you feed yourself with fat or with carbohydrate. Buffhead.
Now you don't have ATP generation because you're minimizing the gradient.
No, because it's... Oh, fuck me. Wow. When does the uncoupling protein translocate to the membrane, insert itself across the membrane and start leaking out H+, when there's too much? Does that compromise the ability to make ATP at the rate that it's required? No, it fucking doesn't. Jesus Christ, Michael.
That generates ATP, and you have this buildup of any...
I hope people are starting to see how stupid this boy really is. How stunningly, unbelievably stupid this boy is. It's my pleasure to point it out to you, by the way. Carry on, Michael.
NADH and then the ROS, which also, again, the ROS starts to get dissipated to a large extent through the uncoupling protein. The uncoupling proteins are there to minimize ROS and also to generate heat. So
yes,
in situations of stress or excess ROS generation, uncoupling proteins are literally there to dissipate the ROS.
They're literally there. Does that mean they're physical things? Bits of kit? Machinery, Michael? Just like everything else you've spoken about, which are physical things, kit, bits of machinery. Michael? Yeah, I thought so.
To protect the mitochondria.
Yes, good. Okay, so you've just eviscerated your own argument. Okay, good.
In certain situations. Now,
but say again, though, because that's important.
So again, we have this build-up. Now what we're left with is decrease.
Don't forget to say literally again, though, as well, because it's important to say literally.
ATP
like
P, because the uncoupling protein is there because of the ROS. Maybe we have mitochondrial damage if our mitochondria membrane is full of polyunsaturated fats, and we have this excess of NADH. So what happens when we have this excess of NADH?
We don't.
So we're going to come back over here to the Krebs cycle. Now we have the Krebs cycles producing this NADH for...
See, why would you think that we're going to have an excess of NADH, Michael? What's going to cause an excess of NADH? Well, wait. We won't wait because there'll be no explanation for that. There isn't one.
For us, right? But what does it need to produce the NADH? It needs NAD+.
Yeah, you've mentioned that already. That's why it's always there in the amount that it's needed.
So we're basically building up this NADH, and we don't have enough NAD+ to run these reactions. So what happens?
No. When you've got enough NADH, then the NAD will be effectively reduced in that way. No problem. And the energy will be liberated, made available for another round of carrying said protons and electrons, reducing equivalence. No problem. Again, it's almost as if it's something that's been worked out by the anthropic principle and natural selection pressures over 13,800 million years, Michael.
The system gets backlogged here, right? So you're going to get...
No, wrong. It doesn't.
Get a buildup of these different metabolites because there's not enough NAD+ here to run isocitrate dehydrogenase or pyruvate dehydrogenase.
Yeah, it's almost as if the thing has a throttle on it. Like it should do, like any bit of machinery should have, to stop that flywheel from spinning out of control. That bit of kit, that physical bit of machinery there, Michael. That's a good analogy, isn't it? What's your point? Besides no point as usual.
Dehydrogenase. So acetyl-CoA gets backed up here. So you get this excess acetyl-CoA to CoA. You get a buildup of citrate all the way. back, and then you also get a buildup of NADH with nowhere to go. So
yep, so what?
What happens? The buildup of NADH, the buildup of acetyl-CoA shuts down pyruvate dehydrogenase.
Yes, we've already covered all of this. We understand. It happens because it's supposed to.
And then the buildup of citrate goes and shuts down the enzymes in the enzyme in glycolysis.
Yes, we've already covered this. We understand.
Phosphofructose kinase 1, and then also that buildup at phosphofructose kinase 1, that buildup of its substrate, which is glucose 6-phosphate, then can shut down hexokinase, which can impair the movement of glucose into the cell, because you have
right, the very thing that you said does not occur, Michael. The very thing that is the actual terminal endpoint, the whole reason this fucking cycle exists. Because too much glucose in a cell is toxic to the cell. Good, I'm glad we got there. Now we understand the Randle cycle, and Mike still doesn't. He still thinks this is unimportant.
You have this buildup of the glucose 6-phosphate and nowhere for this to go. Or you have somewhere to go because there's the phosphofructose kinase 1 is...
Mike is also presenting this information like the cycle either runs or doesn't run. He didn't say that explicitly, but that's what he's kind of inferring here, that suddenly the thing is shut off. No, the inhibition is maximized when the actual spinning rate of the wheel is maximal. It is actually happening at a maximum rate. The energy that is required is being produced at its maximum rate. There is no problem here. It's a limiter because there should be one.
Still working to some extent, but its function has been strongly decreased. So you basically get a buildup there, but you have this huge inhibition of pyruvate dehydrogenase.
Yes, which is indicated.
And this buildup of acetyl-CoA.
Yeah, you've said that.
So what are you left with essentially? You can get a buildup of pyruvate.
Yes, which would then be reduced to lactate and exported by the MCT transporter to the blood, and then that can be transported around the body as a second messenger hormone-like system, and also to provide energy to cells either immediately adjacent to the cell that's leaking out, or indeed cells that are vastly distant from that cell because they're being transported around in the blood. Also, the liver takes it up and starts to use that as a substrate for gluconeogenesis. It's called the Cori cycle. What's next?
So now you can't oxidize carbohydrate effectively through the Krebs cycle.
What do you mean effectively? Another value judgment statement. The exact amount of carbohydrate oxidation that is allowed is appropriate to the needs of the cell at that time. This whole system works in an integrated way precisely in order to manage that situation.
You have a decrease of ATP generation at the cell to some extent.
No, you don't. False. Absolutely false. No such thing occurs.
If there's a large amount of ROS and uncoupling proteins had to be increased, you have an increase in ROS, and then you have impaired insulin sensitivity because you have that whole backlog through.
Nonsense.
This is the Randle effect.
No, it isn't. That's a complete misrepresentation of the Randle effect by a complete charlatan with absolutely no understanding of the first principle of anything he's talking about whatsoever.
This is essentially the Randle effect.
No, it isn't. It still isn't.
What happens when you have an excess of fatty acid oxidation?
No, you don't have an excess of fatty acid oxidation. It does not occur, Michael. Wrong.
And a large part of it stems around that ratio again.
No, false. Absolute nonsense.
Of FADH2 to NADH.
Nonsense.
That with fatty acid oxidation, there's a comparatively higher ratio of FADH.
You've said that already, and it was wrong the first time and the second time and the third. It's still wrong, Michael. No.
To NADH than there is in carbohydrate oxidation, and it causes this whole backlog. And basically, you get stuck oxidizing fatty acids because
you're not stuck with anything. You're oxidizing fatty acids, which is entirely appropriate. And your cell is blockading the use of glucose because it's not required. And in fact, it's contraindicated in the cell at concentrations above that, which are also only occur when you take in too much glucose, which is any at all. Ergo, you shouldn't do that. Job's a good one. Join us next week when someone else will be wrong on the interwebs, but not as wrong as this clown. All right, finish off then.
Pyruvate dehydrogenase gets shut down. And then essentially, if you do have a buildup of pyruvate, then that buildup of pyruvate could possibly go to lactic acid fermentation.
No, not lactic acid, lactate.
And produce a smaller amount of ATP from carbohydrate than you would if you had fatty acid oxidation.
So what? There's enough ATP being produced. That's why the system is occurring.
Obviously, glycolytic flux gets decreased as well. So this is...
As it should in that circumstance.
This is the Randle cycle. This is the fatty acid oxidation inhibition.
No, that's your complete misrepresentation of it, Michael. Your irresponsible, ridiculous, and incompetent assessment of what you think the Randle cycle is. It's nothing of the sort.
Of carbohydrate oxidation. These are the mechanisms here. It's what happens at the...
You mean the machinery? The bits of kit that make up the metabolic machinery, Michael? That's what I thought.
Electron transport chain and what's going on at the Krebs cycle. And again, it stems to that FADH2 and NADH ratio. It's extremely...
No, it doesn't. Not at all. False.
Important. Now...
No, it isn't. False.
Last thing I want to talk about here is what does this actually look like?
In mice? Great, tell us all about mice, Michael. Next time I'm talking to a mouse about its physiological requirements and dietary requirements, I'll be sure to mention this mouse study. Fucking idiot.
In research studies. So what they
on mice
say is in mouse models, the genetic suppression of pyruvate dehydrogenase and cardiac and skeletal muscles results in dramatic effects in male pups, which die on weaning. But
So what?
But not in female offspring. These pyruvate dehydrogenate deficient female mice can survive if fed a high-fat diet, but they then go on to develop muscle hypertrophy and heart dysfunction.
So?
In contrast, upregulation of pyruvate dehydrogenase kinase by genetic manipulation or in response to high-fat diet, starvation, or insulin deficiency keeps glucose oxidation at a low level, whereas fatty acid oxidation is increased. So in both these states, if there's a mouse, they have mice which have...
Again, next time you're talking to a mouse about its dietary requirements, make sure you mention this study in a murine model. Absolutely, in a mouse model. Got some data on humans at all, Michael? No? Off you pop to fuck then.
Have had their genes adjusted, or they've played around with their genes so that the pyruvate dehydrogenase...
It's almost as if the pyruvate dehydrogenase complex exists in human beings for a reason, in exactly the same way it exists in mice for a reason, and we shouldn't knock it out. Okay, good. What's your point? Besides, no point still.
Hydrogenase in their muscles basically has much significantly decreased function. The male mice will die, but the female mice, essentially, they can only eat a high-fat diet, and they'll...
You've said this, Michael. You read it out word for word, not 2 minutes ago.
They'll be able to live, but over time, they develop muscle hypertrophy and...
You said that already, remember?
Heart dysfunction. So this muscle hypertrophy, this isn't a good thing. This is actually a response to poor energy production at the muscle cells. They try to...
That's why you shouldn't knock out pyruvate dehydrogenase complex. It's there for a reason.
Increase the number, the muscular fibers, or perhaps there's a buildup of metabolites within the muscle cells, which could form the hypertrophy. And you also get heart dysfunction. And I think this occurs because, as I was talking about, when you have an excess of fatty acid oxidation without...
You don't, ever.
The glucose oxidation, what winds up happening is you can get at a certain threshold, a large amount of ROS.
You've spoken about that, and there's a way that the body deals with it. Remember? Not 5 minutes ago, you explained that to us.
This large amount of ROS can lead to...
So what happens when you uncouple? The ROS level is controlled, so it doesn't build up. That's the whole point of the uncoupling protein. Remember? Fuck me.
To upregulation of...
There is a homeostatic range in which these things exist, and they're maintained by homeostatic processes that have evolved over a very, very fucking long time. My God, this boy is so stupid it hurts.
the uncoupling proteins and basically a decrease in the production of ATP?
No, because it happens when the system is operating at maximal capacity, idiot.
So you have an energetic dysfunction.
Besides, the concentration of ATP in a cell remains constant pretty much at all times, within a very, very narrow band, precisely because of homeostatic mechanisms and the adjustment and plasticity of the rate of metabolic flux, Michael. It's an integrated system. It works really well. It's had a long time to work out how to do it.
And then a large amount of ROS can also damage the cells and damage the mitochondria.
It could if it was allowed to build up. It's not, though, because the uncoupling protein disallows that from occurring, you fucking idiot.
So over time, the high-fat diet allows them to survive, but it doesn't allow them to thrive because they're still stuck with an energetic...
Mice are not evolved to live on a high-fat diet, Michael. Humans are.
Deficiency and or damage to the mitochondria from an increase in ROS because they can't...
Neither are mice evolved to thrive and survive to any level without pyruvate dehydrogenase complex, and neither are humans. What's your point?
Effectively oxidize enough carbohydrate.
Effectively and enough. More value judgment statements without support or meaning.
Again, there's thresholds here, so it's not just if you're oxidizing fat at all, it's bad, because the heart does oxidize fat.
Of course it does.
To a large extent, but it's ratios. It's how much fat is the heart oxidizing versus carbohydrate.
Well, less for the heart, because the heart runs better on a different makeup of substrates than does, for example, a muscle tissue or an eyeball tissue or a toenail cell tissue at the cuticle where the toenail is being produced, for example, or a hair follicle cell. They all prefer different makeups. Luckily, the human body is able to supply all the nutrients that is required to the cells in the blood, fat, protein, and carbohydrate, such that the cells will extract and use those things at the level they need them. Okay? And you don't need to consume carbohydrates to have carbohydrates in your blood, because gluconeogenesis, Mike. All right, what's next?
Etc. So there's some nuance to the picture, but essentially inhibiting carbohydrate oxidation leads to severe issues.
In those pyruvate dehydrogenase knockout mice, yes. Got some studies on humans on that? No? Back to fuck you must pop then.
The other thing they talk about is basically inhibiting upregulating pyruvate dehydrogenase kinase. Now,
you've said this already, remember? It was irrelevant the first time.
Again, you can do it through genetic manipulation, or you can just create a high-fat diet.
Yeah, you've said this already. You read it out word for word.
Undergo starvation or have insulin deficiency, which could be like a state like diabetes. This could be intermittent fasting. This could be keto or carnivore.
Or it could be none of those things, because insulin deficiency is a construct and a concept, and it's ridiculous.
And essentially, now, alleviate
the Randle cycle activation, and you alleviate the so-called insulin resistance. Simple. If you feed yourself unnecessary exogenous carbohydrates, you risk a problem. It's your own funeral.
To some extent, if you're doing carnivore and it's very high protein, this may be altered a bit because of an excess of gluconeogenesis.
Yeah, and maybe not too.
So even if you're high fat, you may still have some carbohydrate, but there's more problems with this, and it's tangential. But essentially, this will help keep glucose oxidation at a low level, and then fatty acid oxidation is decrease. Now, they go on to say that this situation mimics a state of metabolic inflexibility.
Again, that's a value judgment statement, isn't it? You don't need to be flexible metabolically. You need to feed yourself what is metabolically appropriate to feed yourself with, and that is the muscle meat and associated fat of large ruminant animals, grass-fed. If you please, thank you very much. We're done here. You don't need to be flexible in the way that you're talking about. It's contraindicated. The pyruvate situation that you're talking about there, the Randle cycle, the whole thing is proof of that. It shows how we have evolved and the reasons we have evolved that way. It's clear, it's unambiguous, it's not open to your ridiculous, childlike and incompetent interpretation, Mike. You're a buffoon, you're a fool, you don't know what you're talking about. You need to shut the fuck up permanently and go and clean those fucking bedpans, nursey.
Essentially a failure to adapt metabolism to the fasted to fed state transition, which is a feature of insulin resistance. Again,
no, it isn't, because insulin resistance is a construct.
And this situation mimics a state of metabolic inflexibility.
You said that, remember? Not 2 minutes ago. I've dealt with it. What's next?
Essentially, hold on, let me just turn the light on.
Fuck me, really?
Essentially, when you have an excess of fatty acid oxidation due to an upregulation, or if you have an excess of fatty acid oxidation, and which can cause an
Oh God, this is painful, isn't it, boys and girls?
Upregulation of pyruvate dehydrogenase kinase and impair glucose oxidation, which could be caused by high-fat diet, starvation, or insulin deficiency.
You've said all of this. None of it is correct interpretively or relevant to what the Randle cycle is or is not and why it exists, Michael.
You enter a state of metabolic inflexibility where you're forced to oxidize.
You've said that. It was stupid. You've said it twice already. It was wrong and stupid the first 2 or 3 times. It's still just as stupid and wrong now.
As fatty acids. So you're literally metabolically inflexible.
Literally inflexible.
This flies in the face of some of the comments I've seen by low-carb supporters or low-carb gurus.
No, it doesn't, because this is a study on mice. So fuck off.
Say that oxidizing fatty acids and minimizing carbohydrate oxidation leads to a state of metabolic flexibility.
Who said that? And who said it's required? I've never said that, and neither is it required. It's contraindicated. You don't need flexibility.
This is just basically is wrong. It's basically incorrect.
It would be if I'd said it, but I haven't. So I don't know what your problem is here, Michael. Who the hell said that feeding yourself fat gives you metabolic flexibility? And who said that that was a good thing? Please point to it. Give us a timestamp and a video URL so I can go and tell them they're wrong.
Because the excess fatty acid oxidation through the mechanisms that I just went through.
No, not excess. It doesn't happen, remember?
And also, again, I'm not even saying this. What the researchers are saying here.
No, you don't understand what the researchers are saying and what they're not saying, Michael. And people writing opinion pieces like this are not researchers. Maybe they are researchers that are doing research in other works. This particular piece of work is an opinion piece, and it's fucking stupid from start to finish, Michael. It's inane. And you're a fucking buffoon for having sucked this ridiculous lollipop. This ideological claptrap that this paper is.
Is it creates a state to some extent of insulin resistance.
No, it doesn't. We've dealt with that.
And an inability to oxidize carbohydrate effectively, which
is wrong again. Effectively. What does that mean?
The metabolic inflexibility.
No. We don't need flexibility.
So again, shutting down.
Again, we got it the first 3 times. It was stupid the first 3 times. You want to go through it again?
Pyruvate dehydrogenase either genetically.
Yes, you've said this. Fuck me. Really? Really? Again?
Or upregulating pyruvate dehydrogenase genetically, or by increasing high-fat.
Really? Again?
High-fat feeding, inducing starvation, perhaps fasting, and then also insulin deficiency creates a state of metabolic inflexibility.
Nonsense.
And insulin resistance.
Nonsense.
And in an extreme at an extreme level with blockage of pyruvate dehydrogenase, you basically get death in the
yes, you've said that.
Offspring of
in mice, yes,
the animals that were genetically modified to have that deficiency.
Good thing no one's suggesting that we will knock out our pyruvate dehydrogenase complex genetically.
See. Or like muscle.
All we're suggesting is eat a species-appropriate, species-specific diet, that being the muscle, meat, and associated fat of large ruminant animals grass-fed, and not plants or carbohydrates. in any amount ever. And if you do, that's your own choice, but be aware that it's not ideal for you. And it will cause a problem. The Randle cycle. Anytime you mix carbohydrates and fats together, it's almost guaranteed to activate the Randle cycle to some degree for a period of time, which will absolutely subject you to inflammatory process and fat storage. Okay? Okay? Right. What's next?
Failure to a large extent with hypertrophy and dysfunction over the long term with the high fat feeding. So again, this is a feature. This is what happens on extreme levels in these situations with shut down.
Fuck, this is incredible, isn't it, kids?
Pyruvate dehydrogenase.
By which I mean totally lacking in credibility at all.
Now, say
absolutely though, this is a boy who thinks himself qualified to say how wrong I am about everything I have to say about the Randle cycle.
If we upregulate pyruvate dehydrogenase, what they say here is conversely, the blood glucose level in starved pyruvate dehydrogenase.
Have you not done with this paragraph yet, Michael? Are you still repeating parts of it? Wow!
Kinase 4 deficient mice is lower than in wild types, probably because the active pyruvate dehydrogenase diverts pyruvate, a gluconeogenic substrate, to acetyl-CoA. These observations underlie the crucial role of pyruvate dehydrogenase in glucose and lipid homeostasis.
Yeah, there you go. It's almost as if the thing's evolved for a purpose, that purpose being homeostasis of the organism. Fuck me, it did. Same thing's true in human beings. Shall we move on now?
So essentially, what they're discussing here is that...
Fuck, really? I suppose it's no shock that Michael has to explain everything 5 times for his unthinking audience, in his own unthinking manner. His audience, by the way, of 184 subscribers. Mr. Expert. I mean, sure, we've got to start somewhere, absolutely. But I wonder why you're just getting no traction whatsoever, Michael. I wonder why no one's interested in what you've got to say. I wonder why you felt you had to try and pick on me for some traction. That's backfired on you, hasn't it, son? Anybody else want to have a crack at me? Please do. I'll be waiting.
If you downregulate pyruvate dehydrogenase kinase, which is, again, that's the enzyme that...
Again?
kind of blocks pyruvate dehydrogenase. So if you're downregulating this enzyme, you upregulate pyruvate dehydrogenase, and in doing so, it directs the products from glycolysis, which is pyruvate, to becoming acetyl-CoA and entering the Krebs cycle. And that basically, number one, that essentially would increase insulin sensitivity to some extent, so you would have more glucose being able to flux through.
Insulin sensitivity is a construct, Michael, still.
The Krebs cycle, but it also can minimize the gluconeogenic substrate, which is pyruvate, which can basically be turned into glucose and put out into the bloodstream by the liver. It basically moves it into being oxidized through the Krebs cycle. And again, these examples here, they say these observations underlie the crucial role of pyruvate dehydrogenase.
Yeah, we can see that's what they say, Michael. We can read that just as well as you can and understand it 10 times better than you ever could hope to. Shall we move on now?
In glucose and lipid homeostasis. So these are just going to show the mechanisms that I just described.
The mechanisms, the machinery, the metabolic machinery. Yes, Michael, good.
What actually happens in real physiology if you alter...
Yeah, real physiology. In a reductionist fashion put together by an itinerant crackpot like yourself with no fucking idea what you're talking about or how to interpret what you're looking at. Good.
This enzyme's function in mice or rats.
Yeah, good. Well, we'll make sure we tell the mice and rats all about this next time we're having a discussion with one.
What you wind up seeing is if you decrease pyruvate dehydrogenase...
Fuck me, really? Wow! Tell us again.
Heavily, you're forced into fat oxidation.
Yes.
And if you upregulate pyruvate dehydrogenase heavily, you're forced into glucose oxidation. So,
fuck, that's a shock, isn't it, boys and girls?
Pyruvate dehydrogenase is that switch, and it's also the spot where the Randle cycle is through various mechanisms affecting its switch. So if you have...
And there are a bunch of effects of this on a mitochondrial and cellular, thereby also on a tissue level, organ system level, and organism level as well. Thank you and good night. Fuck me.
Have an excess of fatty acid oxidation, pyruvate dehydrogenase is getting shut down, and then
oh, God. Nearly there, boys and girls. He's nearly done.
Carbohydrate oxidation and uptake by the cells gets shut down, kind of through a backlog effect to the cells. So that's essentially it for this paper. That was what I wanted to cover for the Randle cycle. Hopefully this was helpful for you guys.
Right, so all you've done there, Michael, is what you did say of any value, which was almost nothing, backed up absolutely everything I have had to say about the Randle cycle in the past and will continue to say in the future because it's still correct. You have decimated your own ridiculous argument that I had anything wrong about the Randle cycle at any time, because I didn't. You've misrepresented the thing completely. You've shown yourself to be an ass monkey, a fuck trumpet, and a reductionist of the highest order. You've shown your level of incompetence, which is extreme. You've made yourself a laughing stock of my entire, much, much larger supporter pool than your 184 subs, by the way, Michael. You should be embarrassed to show yourself in public ever again. I hope you don't. I hope you learn something from this. I hope you get your ego under control at some point in your life, son. And get a grasp on your own level of incompetence. You're summing up now, so we don't need to sit through the rest of your summing up. We're done here. Thank you, boys and girls, for your patience. I know it's been a very long haul, nearly 2.5 hours to get through all this ridiculous nonsense. I hope you learned something from it. I hope it was of value to you. Join me next time when someone else will be wrong on the interwebs. Have a crack, though, boys and girls. Anytime you fucking like. I'll be ready and waiting to deal with your ridiculous fucking nonsense. See you then. Bye for now.